Number 4, for the function f of x equals natural log of x over 9x, find f double prime of x, and then find f double prime 0, f double prime 2. Now be careful here, you cannot divide out those x's because one of those x's is within a log. It's the argument of a log, a natural log, and you can't reduce that. So we just have to go ahead and take our derivative using the quotient rule. Denominator, 9x. Derivative of the numerator, 1 over x. Minus the numerator, natural log of x. Derivative of the denominator, 9. Over the denominator, 9x, all squared. Reducing these x's, I'm going to be left with 9 minus 9, natural log of x, all over 81x squared when I do 9x times 9x. Now I recognize that both terms in the numerator have a 9 in common. 1 minus the natural log of x would be left over. And I have an 81x squared in my denominator. This 9 can divide into this 81, leave a 9 in the denominator. So my first derivative is 1 minus the natural log of x over 9x squared. Now they want me to take the second derivative, so I'm going to use this expression and the quotient rule. Denominator, 9x squared. Derivative of the numerator, 0 minus 1 over x, minus the entire numerator, so I'll put it in parentheses, times the derivative of the denominator, 18x, all over 9x squared, quantity squared. So a little cleanup again. I've got a 9x squared, and this is going to just be a negative 1 over x. And here I'm going to move my 18x to the front so that in the next step I can distribute it. So minus 18x times 1 minus the natural log of x. All of that is over 9 times 9, 81, x squared squared, x to the 4th. All right, so this x is going to reduce with this x. It's going to leave me a 9, an x, and a negative 1. So that's going to give me a negative 9x. Now I'm going to distribute minus 18x plus 18x, natural log of x. All of that is over 81x to the 4th. These are like terms. Negative 27x plus 18x, natural log of x, over 81x to the 4th. And it looks like all of these terms have a 9 in them and an x in them. So I'm going to factor out a 9x. It's going to leave me a negative 3 plus a 2 natural log of x over 81x to the 4th. And now since this is a factor 9x, I can reduce it with the denominator. 9 into 81 is 9. X into x to the 4th leaves x cubed, and that's my final answer in simplified form. It's negative 3 plus 2 natural log of x over 9x cubed. Negative 3 plus 2 natural log of x. All of that is over 9x to the 3rd. Now we're going to use this to find these values. Again, the more simplified it is, the easier it is to evaluate, but sometimes the simplifying is the most difficult part. So I've selected f double prime of 0 as undefined, and here's why. There are a couple of problems. if you put 0 into negative 3 plus 2 natural log of 0 over 9 times 0 cubed, well, this is undefined. Try it on your calculator, you'll see. This is also undefined. So there is no f double prime existing at 0, so it's undefined. So now I need to find f double prime of 2, so I put that into my second derivative. It's going to be negative 3 plus 2 natural log of 2 divided by 9 times 2 to the third. So that's going to be 9 times 8 in the denominator. That's a 72. And the numerator is negative 3 plus 2 natural log of 2, and I'm going to have to get a decimal for that. The natural log of 2 is not going to be a nice number. E to what power is 2? So it's going to be a decimal. So I'm going to take out my calculator here. And it's a lot easier on your calculator because you could just enter it just like you see it. Put parentheses around the numerator, enter it just like that in the TI-32XS. I've got to do the natural log of 2, that's this part. I've got to multiply it by 2, and that's about 1.386. I got to subtract 3 from that. Negative 1.6137, I've got to divide that by 72. Negative let's see, to 4 decimal places. Negative 0.0224. Number 5, find the open intervals where the function is concave up or concave down. Find any inflection point. Well, if a function is concave up, it's going to be bowl-shaped up, and if it's concave down, it's going to be bowl-shaped down. And if it changes from one to the other, the point where it's changing is called the inflection point. So for our graph here, you can see it is concave down until, and they're indicating to you that this is the point where it changes, where x is 1 and y is negative 47 over 3. So it is concave up from 1 to infinity. Remember, when we do intervals of concavity or increasing and decreasing, we only use x values. So it's concave down on negative infinity until it gets to 1. And they're going to be open intervals also. Now, where is the inflection point? Now, the inflection point is a point. That's an ordered pair. That's why they've given us the y value. So 1 comma negative 47 over 3 is our inflection point. Number 6, find the open intervals where the function is concave up or concave down. Find any inflection points. So we've got our curve shape down on the left. We've got our curve shape up on the right. We have this vertical asymptote here at x equals 1, which is not in the domain of the function. We have a horizontal asymptote here at y equals 5. And there's no inflection point because it's changing from down to up at an asymptote, not at a point. So our answer here is that the function is concave up from 1 to infinity. And concave down on negative infinity to 1. Again, using x values only. The function does not have an inflection point because the concavity changes at the asymptote. Now we're going to use the second derivative test to find the open intervals where the function is concave up or down, and we'll find an inflection point by setting the second derivative equal to 0. So if f of x is negative 5x squared minus 5x plus 5, f prime of x is negative 10x minus 5. Now remember, that's the first derivative. The first derivative tells you increasing or decreasing. The second derivative is going to be negative 10. Now this is always negative. Therefore, this original function is always concave down. So that's from negative infinity to positive infinity, and therefore there are no inflection points. Number 8. Find the open intervals where the function f of x equals negative 3x cubed plus 27x squared plus 169x minus 3 is concave up or concave down. Find any inflection points. Again, we're going to use the second derivative. So we take our first derivative, negative 9x squared plus 54x plus 169. F double prime of x will be negative 18x plus 54. We set the second derivative equal to 0. Negative 18x equals negative 54. Divide by negative 18, x equals 3. We put our 3 on a number line, and we find the value of the second derivative, whether it's positive or negative. I'll pick a number like 0 and a number like 5. So I'm doing negative 18x plus 54. So f double prime of 0, negative 18 times 0 plus 54, is going to be 54. It's positive and it's concave up. Now, at 3, it's 0, so it could be an inflection point if it changes from positive, that is, concave up, to negative, concave down. So we're going to put in a 4, so f double negative 18 times 4 plus 54. Well, that's going to be negative 72 plus 54, so it is in fact a negative number. Again, the actual value, less important than the sign, concave down. So this function is concave up, and then it changes to concave down at the point where x is 3. Now, we only know the x value, so in order to find the y value, we have to put 3 into the original function. So we'll go ahead and do that because it's the first thing they ask us is the inflection point. So f of 3 is negative 3 times 3 cubed plus 27 times 3 squared plus 169 times 3 minus 3. So that's going to be negative 3 times 27 plus 27 times 9 plus 169 times 3 which is 507, and then subtract 3. So that's negative 81 plus 27 times 9, 243, plus 507 minus 3. So all of that totals up to negative 81 plus 243 plus 507 minus 3 is 666. That's my inflection point. And so 3,666 is my answer. And by the way, I didn't make that number come out that way. Just a coincidence, even though you may think calculus is the devil at this point, and I totally understand why. All right, so here we go. Let's keep going. We got a 3 here, and it's concave up on the left and concave down on the right. So it's concave up from negative infinity. By the way, it's a polynomial function, so it doesn't have any gaps. It's continuous everywhere until I get to 3. And it's going to be concave down from 3 all the way to positive infinity. Number 9, find the open interval where the function is concave up or concave down. Find any inflection points. Now for this function, I think I'm going to go ahead and multiply it out because it's just a lot easier and it's not nearly so messy. So I'm going to take my x plus 2 times my x plus 2. That's my x squared plus 4x plus 4, because remember, you fool that out. So this is going to be 2x times x squared plus 4x plus 4. Now, if that power is anything other than a 2, you're probably best just leaving it, if it was a 3 or a 4 and you had to multiply out a bunch of these binomials, just use the product rule, okay? But in this case, I think it's easier. 2x cubed plus 8x squared plus 8x. Right, so that's a polynomial function. It's just a cubic function, so the derivative is not that hard. F prime of x is 6x squared plus 16x plus 8. So I'm using the power rule on all of these. And then the second derivative is 12x plus 16. Set the second derivative equal to 0 to find your point of inflection, if it exists. This time it's a decimal, no big deal. X is divide 4 into that, divide 4 into that, so negative 4/3. I put that on a number line, negative 4/3. To the right of that is a number like 0. Now, that's negative 1 1/3, so I'll just pick something like negative 10. Anything as long as it's to the left. I have to put that into the derivative, which is 12x plus 16. So I'll put that down here so I can remember it. I'm going to put a negative 10 in there. So 12 times negative 10 plus 16, well, that's negative 120 plus 16. So it's negative on this side, okay? Concave down. And then I'm going to put a 0, 12 times 0 plus 16. Well, that's just going to be a 16, so it's positive over here, so it's concave up. So the function is concave down from negative infinity until you get to negative 4/3, and they're going to want that as a fraction, not as a mixed number or decimal. It is concave up from that same point, negative 4/3, until the rest of x infinity. Now, the point of inflection, if it's going from concave down to concave up, that point is where it changes, and that's what we have. So I have to put negative 4/3 in the original function. So I need to find f of negative 4/3. This is my point of inflection. So it's 2 times negative 4/3 and negative 4/3 plus 2. And I'm just going to go ahead and put it over 1 so I can get my common denominator there, squared. So that's going to be negative 8/3, negative 4/3, and 2/1. I need a common denominator of 3, so I'm going to just multiply the second one, top and bottom, by 3. So negative 8 over 3 times negative 4 over 3 plus 6 over 3, and all that's going to be squared, is negative 8 over 3. Negative 4 plus 6 is 2/3, okay, squared. So negative 8 over 3 times 4 over 9, now be careful, you got to square the 2 and the 3, is negative 32 over 27. And remember, the first point was negative 4 over 3, that's the x value. Negative 32 over 27 is the y value. Now, if you have a calculator, the calculator you're supposed to have, it has a fraction key on it, and you are welcome to use that. I am not going to check your arithmetic on fractions or make you show the work on that. You can do that on the calculator. Number 10, find the open intervals where the function f of x equals 19x plus 19e to the x is concave up or concave down, and find the inflection points. So this time we have a function with an exponential. Remember that the derivative with respect to x of e to the x is e to the x. So that makes the derivative pretty easy to do. So we get 19 plus 19e to the x. That's the first derivative. Now there's no x there because we took the derivative of 19x. F double prime is going to be 0 plus 19e to the x. So our second derivative is 19e to the x. Now we need to know where 19e to the x equals 0. Well, if you remember, e to the x never crosses the x-axis. It's never 0. So it does not have an inflection point. Now, what do we know? The function is concave up or concave down. Well, it seems like it's going to always be positive. All we have to do is pick any value, and look, e to the x is going to be positive because e is a positive base that's approximately 2.7. If you raise it to a power, any power that's an integer, you're going to get a positive number. So it is always concave up, never concave down. Now be careful, if that was a negative 19, it would always be concave down. So negative infinity to positive infinity. That is assuming we don't have a choice for always up. Yep, that's it. Number 11, find the open intervals where the function f of x equals the natural log of x squared plus 4. Where is it concave up or concave down? Again, second derivative test, greater than 0, concave up, less than 0, concave down. Remember that the derivative with respect to u of ln of u is 1 over u times du. So I've got to use a chain rule on this. F prime of x is 1 over x squared plus 4 times 2x. Don't forget the 2x. Whenever you have a differentiable function within another function, you have to tack on that chain rule. So that is 2x over x squared plus 4. Now we have a function without a natural log. We've got a rational function, and we've got to use the quotient rule. So we've got our denominator, x squared plus 4, times our derivative of the numerator, 2, minus the numerator, 2x, times the derivative of the denominator, 2x, all over the denominator, x squared plus 4, quantity squared. That's that quotient rule, comes up over and over and over. Distribute this so I can combine like terms, 2x squared plus 8 minus 4x squared. All of that is over x squared plus 4 quantity squared. Combining these two like terms, negative 2x squared plus 8 over x squared plus 4 quantity squared. Now, we don't ever have a denominator equal to 0, so this function, the second derivative, is equal to 0 only if the numerator, negative 2x squared plus 8, is equal to 0. So negative 2x squared equals negative 8, divided by negative 2, x squared equals 4 for two values. X is plus and minus 2. Remember, if you were to factor this, it would be x plus 2, x minus 2. That's where you get plus and minus 2. Plus the square root property says when anything squared is a number, then that thing squared, in this case x, is plus and minus the square root of that. So now I'm going to copy my second derivative so I'll have it handy down here because we're going to put these values on a number line, 2 and negative 2, and we're going to see what happens between them. So negative 2 would go on the left and positive 2 would go on the right. I must pick a test point in here like 0, a test point over here like 4, and a test point over here like negative 4. Now remember, these intervals are from negative infinity to negative 2, then from negative 2 to 2, and from 2 to positive infinity. So the question is, does the second derivative change signs at these two places where it's actually 0? If it does, you have an inflection point. So if I put a negative 4 into my derivative, I have negative 2, negative 4 squared, plus 8, over negative 4 squared plus 4 all squared. Well, that's going to be negative 2 times 16 plus 8. And all of this down here is squared, so this is going to be positive. And this is going to be negative. So a negative over a positive is going to give me a negative, meaning that it is concave down over here. Okay? Now we're going to check in between. We're going to check the 0. That's going to be a lot easier to check. I'm going to get negative 2 times 0 squared plus 8. That gives me a numerator of 8. And 0 squared plus 4 squared, which gives me a denominator of 4 squared. That's a positive over a positive. This one's positive, so it is concave up here. So we know we got an inflection point at negative 2 because it was down and now it's up. We don't know about positive 2 yet. We have to check positive 2. If it changes again to negative, you have a second inflection point. So we take our 4 and plug it in to negative 2 times 4 squared plus 8 over 4 squared plus 4 squared. The bottom is going to be positive for sure. The numerator is going to be negative 32 plus 8. It's going to be negative. A negative over a positive is a negative in this interval, so it changes from positive, that's up, to negative. There's an inflection point there as well. So the function has inflection point at, well, there are two of them. We've got to evaluate the function at negative 2 and 2. So I'm going to create a little space here. The function at negative 2, the function at positive 2. So the natural log of negative 2 squared plus 4 is the natural log of 4 plus 4, the natural log of 8. We're not going to change that to a decimal. We're just going to leave it like that. And because I'm squaring it, the natural log of 2 squared plus 4 is also going to be the natural log of 8. So we got negative 2, natural log of 8, positive 2, natural log of 8. Those are our inflection points, and they want us to put a comma between them. Negative 2, natural log of 8, comma, 2, natural log 8. So originally when we did our second derivative, remember our second derivative test? we had that it was negative here, positive here, and negative here. So we had that it was concave down, concave up, concave down. So we set an inflection point here and here. So the function is concave up only from -2 to 2. And the function is down, remember, from -infinity until it got to -2, and then again from 2 to positive infinity. Number 13, find the critical point for f and then use the second derivative test to decide whether the critical point is a relative maximum or a relative minimum. So if f of x is -x squared plus 4x minus 4, its critical value is where f prime of x is equal to 0. So f prime of x is -2x plus 4. -2x plus 4 equals 0. -2x is -4, so x is 2. So something's happening at 2, and they want us to look at the second derivative to decide if that critical point. Now remember that the critical point is a point, so we know that x is 2. We need to now find f of 2. So that's going to be negative of 2 squared, be careful, no parentheses this time, plus 4 times 2 minus 4. That's going to be -4 plus 8 minus 4, so that's going to be 0. So our critical point for f is 2, 0. Since the value of f double prime at the critical number is, okay, so now they want us to find f double prime at 2, but let's find f double prime first. So remember, f prime was -2x plus 4, so f double prime is -2. Now that's always a negative. The relative extreme point is a maximum. Okay, now I'm going to go up here and we're going to talk about why that's a maximum. So look at what this says. The second derivative test says f double prime exists if f double prime is positive, it's a relative minimum. Now, why is that true? Think about this. If it's concave up, it's going to be a minimum. If it's concave down, it's going to have to be a maximum. The second derivative says that this graph is concave down, so that's got to be a maximum. And so that's why this is the way it is. If f double prime is greater than 0, it's a minimum, because concave up would tell you it's at a low point. So that's why it's a maximum. Number 14, if the function is f of x equals 2x cubed minus 6x squared plus 5, use the second derivative test to decide if the critical number leads to a relative max or relative min. Remember, if it is concave down, the second derivative is less than 0, and you have a relative max. And the opposite is true if it's concave up. The second derivative is a positive number, and that critical number is going to cause a minimum. So if we take the derivative of f, we get 6x squared minus 12x. To find our critical numbers, we set this equal to 0. We factor out a 6x, and we get x minus 2. 6x equals 0. If x is 0, x minus 2 is 0 if x is 2. So we do have two critical numbers here. They are 0 and 2. Now we have to evaluate, they want us to evaluate the second derivative at these two numbers. So we can tell by concavity if we have a relative max or min. So remember what that says, that if you have concave down, second derivative is less than 0, you're going to have a maximum. And if you have concave up, the second derivative is greater than 0, and you're going to have a minimum. Kind of seems backwards with what it would be, but think about what the shape looks like. So when we do our second derivative, we get 12x minus 12. Evaluated at 0, it's negative. Evaluated at 2, it's positive. So at the smaller critical value, that is 0, you have a relative maximum because it was negative. And because at the larger critical value 2, we got a positive, we have a minimum there.